All right, it's a few minutes past the hour, so I think we can get started. Today's topic is large detector systems and the discovery of the top quark. So we'll review some sort of continuing along the theme of the course, how particle physics experiments get organized into these larger and larger collaborations, and the modes of collaboration kind of change. We're going to talk a little bit about how these large general purpose detectors, whose development we've now followed from early examples like the Mark I experiment at Spear or the UA1 experiment at CERN, that type of organization, both material organization of the detectors around the interaction point, but also kind of social organization of physicists into collaborations, will really come to dominate the large detector systems that we'll see, for example, in this lecture looking at the Tevatron. I'll talk a little bit about the time projection chamber and how it works. We alluded to that briefly when we were talking about the Aleph experiment at LEP. It's an interesting detector technology, and I think it's worth going through how it works. And then we'll talk a little bit about the discovery of the top quark at the Tevatron, the differing approaches of the CDF and D0 experiments that nonetheless both ended up contributing to this discovery. So when I think about these large detector systems and how they sort of influence and change how physics is done during the era that we're talking up leading up to the present day, it puts me in mind of a kind of an analogous transition which happened over time in the world of fine art. So once upon a time, an artist was someone who was, making with their own hands, sculpture or painting with their own hands, a painting. But over time, we've seen the rise of some artists who kind of play with this idea. An early example would be Andy Warhol, who had these paintings that were kind of informed by consumer culture. And one of the main practitioners of this style of art today is this guy, Damien Hirst, who's a British artist who's made hundreds of millions of pounds selling art to collectors, in many cases, art that he did not personally produce. He makes no attempt to hide that most of his pieces are made in a factory type mode. This picture here is one of his famous dot paintings, of which there are several thousand in existence. He only painted the first couple, then he sort of gave instructions to other painters working in his factory how to do it. So part of the idea behind this art is to play with the idea of sort of modernist conception of authorship. Like, who is really the author of the piece? Is it the guy who had the idea and set up the factory, or is it the guy who actually painted it? And he has this kind of funny quote playing up this distinction, saying, the best person who ever painted these spots was not him, but one of his assistants named Rachel. So he says, the best spot painting you can have by me is one painted by Rachel. And I would argue that this is kind of the style of organization that was typified by the personality-led collaborations that we've already talked about. You could think of the large bubble chamber at Berkeley that the Alvarez group used, right? So we looked at sort of the physics factory that went into producing results from that big bubble chamber. And it wasn't just Alvarez himself, but many physicists doing all kinds of different analyses, and feeding into their analyses was this army of scanners who were looking at the photographs from the bubble chamber and kind of digitizing the information about the particle tracks, et cetera. So Hirst is working in kind of the Alvarez mode. His name is at the top, and the whole thing is kind of done in his style, inspired by his ideas. But he may not be the one actually producing the painting, just in the same way that Alvarez is not the one that may have analyzed the particular photograph that led to the discovery of a specific charmed resonance or what have you. I would argue that the UA1 experiment that we talked about last time was maybe one of the last experiments in this mold. Even though it was a larger collaboration of people and involved different sub-assemblies that were delivered by different groups, it was very clear who was the sort of progenitor of the experiment. Rubio wasn't just a manager, he was the driving force between the construction of the accelerator and the detector, and had sort of like the major insights that made it possible. And it was clear that, should a Nobel Prize be given out for the discoveries of the W and Z particle by that experiment, that it would go to Rubio himself. But I think that mode no longer really exists in particle physics. You can ask yourself, like, who is the big personality behind Atlas? They've had some people who have been longtime spokespersons, people who were instrumental in putting the collaboration together. But I would argue that there's no single person that you can trace the hierarchy back to. In CMS, who is the progenitor of CMS? It's not an easy question to answer. And so that, in that sense, the modern, or maybe I should say postmodern experiment kind of reminds me more of one of these websites you can go to buy like oil paintings to decorate your house or decorate a hotel room or something like that. And the people who are making these paintings are obviously skilled artists, and yet all the emphasis here in the marketing is on the low price and the huge selection that this art prints on demand can offer. So there's a real divorcing of the specific piece of art that you might buy. May not be clear at all who the original author is. And that is also the case with analysis work in these large collaborations. Not only are the individual components of the detector delivered by different people, but it's different people who do the sort of maintenance operation of these things, the calibration of these things, and then maybe yet another different group of people who is putting together the individual physics objects in order to produce the final plot that would go into a publication. And so if there was some kind of a challenge or a question about the result, that question would also propagate sort of backwards through that network. If you have some problem, let's say you're claiming discovery of the Higgs particle and somebody notices an issue with the efficiency of the muon chambers that go into one of the final states involving muons, right? That question is going to propagate back through that network of individuals, probably back to someone who's connected with the original design or construction, or at least the maintenance and operation of the chambers in question. And so it's not just financially or organizationally how the collaboration is put together, but also how scientific knowledge is like derived and perpetuated within the collaboration, really undergoes a phase shift with these large detector systems. So we nowadays in CMS arguably are more like the model of art prints on demand than even Damien Hirst. So moving into the 1980s, collider detectors grow to be large amalgamations of many subassemblies, as we just said. This change in the material nature of the experiments is taking place in concert with changes in the social and epistemic nature of the experiments. In the large, like bubble chamber experiments, for example, of the 60s and 70s, experimenters had to get used to giving up some of their autonomy to operate freely according to their own physics interests in order to adapt to a hierarchical mode of organization. That is, if you wanted to do bubble chamber physics in the Alvarez group, you could try to join and collaborate with them, but the style of the organization was very much driven by the man at the top. But in these large detector systems that are coming to dominate the field in the 80s and beyond, there are still points where people have to come together to coordinate questions about, the physical layout of the detector, making the different pieces fit together. This provision of services, power, cooling, et cetera, to the detector has to be synchronized between these different groups. But a lot of the work is dispersed in the sense that there really is nobody at the top, right? There may be a spokesperson who's elected by the experiment to communicate with the outside world, communicate with the lab management, and maybe even to resolve some disputes between these individuals. But in no meaningful sense is the spokesperson like giving marching orders to the people building the muon chambers over here and the people building the tracking detectors over here. They are essentially operating independently of one another, largely independently of any hierarchical organization above them. And the only time that they have to sort of be brought into contact with one another is if there's some kind of physical like interference or dependence between their detectors, or later on when you're putting together the results, if there's something that depends the global fit of a muon PT may depend on the details of the momentum resolution of both the tracker and the muon system. And so experts from both will have something to say about that. As far as constructing the experiments, physicists have to increasingly learn to speak the language of engineers and project managers in addition to particle physicists. So you start to see words like critical path, freezing of designs, cost and schedule reviews as a condition of being able to build detectors and do physics, integration aspects, like how can these different subassemblies be made to operate together. You have the emergence of like the data acquisition of the experiment almost as its own separate specialty, because it has to be able to take in signals from all these different types of detectors, which maybe all have their own kind of idiosyncrasies and special cases, and figure out how to make that all work together as a whole as kind of its own subject of expertise, as opposed to the individual subdetectors and how they function. And these concepts extend not just to detector construction, but to physics analysis as well. So you'll hear about in CMS people freezing an analysis note, the same way that you would freeze the design of a detector to allow an engineer to work on making it manufacturable. We talk about sometimes even in the context of analysis, whether questions are really on the critical path to getting the thing approved, or whether it's some kind of a sidetrack that can be put off for later. And it's increasingly important as analyses start to take longer and longer times to see publication, that you manage the schedule of developing an analysis the same way that you would manage the schedule of ordering PCBs or something like that. So let's examine a detector technology which comes into being in the sort of mid to late 1970s in this era of transition to large detector systems. The time projection chamber, or the TPC, where I think you can see some of these issues coming to the fore, and I'll make a few comments about the experiment at SLAC that used this TPC for the first time and how it kind of reflected some of these trends. So what is a time projection chamber, TPC? We talked in a previous lecture about the multi-wire proportional chamber. Remember, the idea there is that you have some kind of gas filling the volume. By choosing the gas appropriately, you can control sort of the number of primary ionization events that occur per unit length of the tracks going through. This ionization probability is also going to depend somehow on the species of the particle and its speed. So the DEDX in the gas is going to depend on those factors, which may be different from particle to particle. And then the idea is that in one of these multi-wire proportional chambers, you can string wires through a gas volume by applying a positive potential to some wires and negative potential to other wires. You can create electric field lines with some desired geometry. And it's along those electric field lines that the products of the ionization are going to fall. And we can have, successive generations of secondary ionizations. So you can build some like gain into your gas detector so that the signals are being amplified at the same time that they're moving through space. At this point, sort of 70s, 80s, drift chambers using wires were, I would say, the standard technology for tracking detectors. The picture here is of an experiment called Argus, which was at the Doris storage ring, which we mentioned a few lectures ago, at Daisy in Hamburg. This was adapted for studying B hadrons and E plus E minus collisions. And so the idea was to surround the interaction point with this drift chamber, which is a sort of general case of the multi-wire proportional chamber. And you typically would build this thing by stringing the wires along the direction of the magnet. So you want this to function as a spectrometer so that you can read off the momenta of the different particle tracks. And you typically would do that by stringing wires along the magnetic field direction. The wires are parallel to the magnetic field. And then the electric field in each cell, where the individual cells are defined by the sort of layout of the anode and cathode wires. Inside this box, the any ionization electrons produced in this box are going to be attracted to this central wire. And if the ionization happens in this next cell over, they're going to be attracted to this one. So each of these kind of defines a separate detector volume logically, even though they all share the same gas mixture. By having this geometry where the E fields are perpendicular to the wire direction and the B field is along the wire direction, you maximize sort of the position resolution in the transverse plane and therefore optimize for the momentum resolution of the particles, right? Your uncertainty on the momentum measurement of the particles is going to be directly related to the position uncertainty of the hits in the chamber. But having the E and B fields crossed in this way also introduces some complication, especially if I want to precisely measure the arrival time of things at this wire. You know, in a multi-wire proportional chamber, I have some discrimination power to see if the track went like far from the central wire or close to the central wire. That's related to the arrival time of the electrons at the central wire. You know, we looked at what the typical drift velocities for electrons in these gases are, and they result in measurable time differences. You know, a particle which goes through here, it will take longer for the electrons to fall onto the central wire as opposed to a particle that goes through very close to it. So at least for small drift distances inside of these cells, you can use the timing of the hit to estimate a little bit how far away the initial ionization events were from the collecting wire. And then you can imagine kind of drawing a circle around this thing corresponding to that time and doing that for the other detector elements along the track. And then the idea is you would try to fit the track so that it's so that the track is tangent to each of those circles as it moves through the volume. That gives you some position resolution, which is less than the wire spacing. But actually this drift time, even inside of these relatively small cells, is not super reliable. And the reason for that is because the B field is pointing, you know, in the direction parallel to the wires here. That means that any drifting electrons are going to feel a Lorentz force, which will tend to make them travel in a little circle instead of going straight to the wire. And that in general tends to broaden and distort the arrival times of the electrons at the collecting wire. It becomes, this time for them to arrive at the collecting wire becomes some complex function of the strength of the magnetic field, the strength of the electric field, the angle and direction and momentum that the electron was originally produced with, and its interactions with gas molecules along the way. So all of these different things, you know, you have a finite precision on each of them, and convolving them all together, you end up with really only a limited ability to precisely time the arrival of the electrons at the collecting wire because of all the different sort of physics effects that are going on. So to summarize, the drift chamber that we have drawn here, it has pretty good position resolution, but not really good time resolution. This guy named Dave Nygren in 1974 had an idea, which was how would the situation change if we actually put the electric fields and the magnetic fields to be parallel to one another rather than perpendicular to one another. And his idea is the following. This is the, he's trying to propose a detector to be used at this positron-electron collider at SLAC, PEP. So there's going to be an interaction point. They want to study basically all of the particles coming out of this interaction. Remember, this time in the mid-70s is when we're kind of trying to elucidate the nature of the strong interaction by looking at 2 and 3 jet events and E plus E minus collisions. It's that kind of physics that he has in mind to measure. And for doing that, you really want to surround as much of the solid angle around the collision point as possible. You want to have good momentum and spatial resolution on the tracks because you're going to try to group these tracks into jets, for example. And you would also like to have some kind of a particle ID capability. So that would mean being able to distinguish between kaons and pions, for an example. And at the point that he's writing this, he thinks that the existing detector technologies leave something to be desired in terms of the ability to reconstruct many different tracks over this large volume. And his idea is to actually align the E and B fields to both point along the beam direction. And this has a couple of interesting things that come out of this idea. So first of all, this is a relatively easy detector to construct in terms of building up these E and B field regions, as opposed to a multi-wire chamber where you have to string these wires along. We talked about how even with a relatively small tension on each wire, which is required in order to keep the wires straight, even when differing voltages are applied to different wires, ends up with huge mechanical forces along the direction that the wires are strung. So you need quite a sturdy vessel in order to hold all that. In Nygren's concept, there are no wires. There's just a foil that bisects the chamber at the sort of z = 0 line here. And then you can hold that foil and the end caps of the tracking volume at two different voltages. This will produce electric field lines which point along the beam direction in either direction from this central foil towards the ends of the chamber. The B field points also along the beam line direction. So on one half of the chamber, it's anti-aligned with the E field, and on the other half of the chamber, it's aligned with the E field. And his idea is that having the magnetic field pointing along the same direction as the electric field means that any ionization electrons which are produced are not going to be able to really diffuse out in the transverse direction because of the presence of this strong B field, right? So any ionization electrons which are produced are going to be constrained basically to loop around the magnetic field lines. If we're producing sort of thermal type electrons, meaning that we're just providing enough energy to ionize them from their parent molecule on average, they're going to be produced with pretty small velocities, and the radius of their helical path through the magnetic field will be very small. Could be, tens or hundreds of microns. And so even over relatively long drift distances, he's drawing here a detector of 2 meters end to end, meaning that each of these drift cells is 1 meter long. You can maintain a really good position resolution on the collected charge at the end caps because of this magnetic field keeping the electrons moving all in the same direction. We can be a little more quantitative about that. So diffusion of electrons in gas follows this sort of typical diffusion equation, thinking first about the uncertainty in the diffusion along the z direction. So that is the beam direction here. We have our normal diffusion equation here where sigma z is going to be related to the square root of 2 times some diffusion constant d times the drift distance here. So a typical example would be methane gas. That's one of the gases that's commonly used in these types of detectors, but other gases, of course, are also possible. For a 50 centimeter drift chamber, so that's only half the size of the one that he sketched on the previous slide, but of course this increases only linearly with the drift distance, and so even a 1 meter drift volume is not going to be appreciably different. If you calculate this, you'll find that the sigma z is about half a millimeter, or 500 microns. People do experiments to measure this. There's a group at Saclay that builds big drift chambers of this size, and they find that the sort of naive expectation from the diffusion equation is borne out, and they're able to measure the arrival of the particles, the electrons, at the end cap of their large drift chamber to have only a dispersion of about half a millimeter. At this point, no one has tried this with a parallel B field, but I hope that you can convince yourself that the existence of a parallel B field shouldn't put any force on the electrons in that direction, and therefore shouldn't really have any effect on this sigma z. Later measurements will bear out that that's indeed the case. It's in the transverse direction that the situation is more interesting. So as we said on the previous slide, with the B field parallel to the electric field, then any ionization electrons which are produced are going to execute helical orbits along the magnetic field lines. And that will result in a suppression of the diffusion constant in the transverse direction. And we can calculate this new diffusion constant in the transverse direction. It's going to be related to the diffusion constant that we measure in Z. That's capital D. But it's then going to be divided by this factor 1 plus omega squared times tau squared, where omega is the so-called cyclotron frequency. It's related to the size of the helical orbits that they're going to describe. That's E times B over M, where if we're talking about the electron signal, as we usually are, that would be the mass of the electron. And then tau is the characteristic time between electron-gas collisions. This will depend, of course, on the type of gas and its interaction cross-section with electrons, as well as on the density of the gas, all else being equal. If I inject more gas into the chamber and overpressurize it, that will reduce the time between electron-gas collisions. But a typical value would be something like 10 to the minus 10 seconds. So if you plug these numbers in, you find that for even atmospheric pressure of certain gases, you can arrange for this factor omega squared T squared to be several thousand, meaning that the diffusion in the transverse plane can be much smaller than the already pretty small diffusion in Z, that you might, in fact, be able to achieve resolutions in the transverse plane of 100 microns or so, given appropriate conditions. So this gives rise to the possibility to build a really intriguing type of detector, which will be called the time projection chamber, because the image that you should have in mind is that there's a spray of particles produced at the collision, and then on each side of this central foil, that image is basically going to float through the time projection chamber at some drift velocity. Remember when we were looking at multi-wire proportional chambers, we saw that you pretty soon achieve this constant drift velocity where the typical energy lost in successive collisions with gas molecules is balancing the energy gained by falling through the electric field. So you have basically a linear drift speed of the electrons through. Any diffusion in the transverse direction, that's like into or out of the page in this diagram, is going to be suppressed by that B field that's pointing along the direction. And so the particle tracks are basically going to fall through space coherently. So imagine this kind of Christmas tree of particle tracks, which is just floating through the volume and collected at the end stage here. So you can have a gas amplification system, basically another multi-wire proportional chamber at the end here with a good position resolution. And if you have some like time measurement capability on this circuit, you can basically see as the track falls onto this amplification region, it will arrive first here and then later here and then later here. And so the time coordinate of the signal arrivals at this last gas amplification stage translates directly to the Z position of the hits along the track, given the drift velocity of the electrons in the gas. So this is a very clever technology. It basically allows you to measure the full three-dimensional array of tracks coming out of an interaction without really any kind of instrumentation in this volume. It's inherently kind of a low mass detector concept, so there's not a lot of stuff in here for tracks to multiply scatter off of or anything like that. And in addition to that, because the collected charge here is going to be related to the number of ionization events, if we choose the right kind of gas and the right sort of pressure of the gas, et cetera, we can also be very sensitive to the DETX along this track, right? The size of the signals that I receive here is going to be related to the energy lost by the initial track as it passes through. So I can also discriminate, for example, pions from kaons over an appropriate momentum range by choosing the type of gas and the pressure of gas inside of here. So it's like a low mass tracking detector with very good transverse position resolution, as well as a particle ID system all in one. This makes it very attractive for certain uses. This is a picture of probably the biggest and baddest time projection chamber, which is currently in existence, which is at the ELISE experiment at the LHC. So this is an experiment whose main purpose is to look at the production of different types of particles in in heavy ion collisions at the LHC, although they have taken data in proton-proton collisions as well. And you see here how this the basic concept can be realized in an actual detector, and it's not that much more complicated than the simple diagram. Some interesting things to note on this picture are the so-called central HV electrode. So that corresponds to Nygren's foil going across the center of the detector. It's not actually a foil here, but actually a thicker, rigid plate that helps to assist with the structural integrity of this thing. And that introduces some sort of gap in the detector coverage. Particles that are produced basically inside this plate you don't measure, but that's a pretty small fraction of the overall volume. There's also these field cages at the outer and inner side. So in order to keep the electric field lines exactly perpendicular inside this thing, you can basically put a bunch of conductors along both the inside and the outside of the volume of the TPC, and then connect each of these rings of conductors with a resistor. And then at one end, you connect that to the central high voltage, and at the other end, you connect it to the voltage at the readout wire chambers. And this sort of enforces that the electric potential lines are like equally spaced and perpendicular throughout the volume. And then that ensures that the electric field lines are equally spaced and remain parallel to the magnetic field lines through the central volume. Then you have these end plates, which are typically segmented in a typical end cap geometry into these sort of dartboard shaped areas. And those are, again, typically something like a multi-wire proportional chamber, so a gas detector with amplification that scales up the signals to make them easier to digest by the electronics. But it doesn't have to be a multi-wire system. You could also imagine having things like GEMS. These are detectors that involve basically a plate with holes in it, where the amplification happens because of electric field lines pointing through the holes, and really any kind of detector which is sensitive to charged particles and from which you can measure an amplitude, that's the DEDX, as well as the time structure of the signal, would be suitable here. This works very well, especially if I want to be able to get the DEDX of many tracks in a coherent way without introducing a lot of mass in there. Probably three of the main TPCs from particle physics experiments are listed here on this table. PEP4, that's the TPC experiment at SLAC that we were talking about. The Aleph experiment at the LEP collider, which used a TPC for its central tracking, and the one that we've been looking at on the previous slide, Elise. You can see that in most of these cases, 2 out of 3 anyways, they're operated just at 1 atmosphere of pressure. The original one was at a higher gas pressure, but that, of course, comes with some complications, having to have things in a pressure vessel. And so successive TPCs basically did away with this idea of operating at overpressure and just operate at 1 atmosphere, which makes life much easier. You can see here what this omega times tau factor comes out to for different TPCs. Aleph here has a omega tau of 7, which is larger than the other two. Here, they were sort of in the range of 1, meaning that the diffusion in the transverse plane is not reduced by a factor of 50 as it would be in the Aleph case, but is sort of more like a factor of 2. Remember, we have 1 plus omega squared, tau squared in the denominator. You can see the typical pad size. These are the individual readout channels at the end caps. Will be something like a few millimeters on a side. At PEP4, 7.5 times 7.5 millimeter readout sections at least a couple of different geometries are used. There's a different amplification factor of the gas, a different number of total pads. And the resolutions that come out of these things are typically in the Z direction, a few hundred to a few thousand microns. So that's roughly consistent with the 0.5 millimeters that Nygren originally guessed based on those large drift chamber experiments at Saclay. and the position resolution in the transverse dimension, which is at least somewhat less than that, typically a few hundred microns up to about 1 millimeter in the case of Elise. So these are not the only TPCs that have been constructed. There are also TPCs working, for example, at RHIC, the relativistic heavy ion collider at Brookhaven. But this kind of gives you the idea of what's typically used. Just like in the case of the multi-wire proportional chamber, you're typically choosing a gas mixture that has something like argon. That's a noble gas that has low chance to resorb electrons from other ionization events, and itself has a large primary ionization component, and then something like methane, which is basically providing the control of the drift velocities as you go through. So this is kind of two of the three components of the so-called magic gas mixture that we talked about a few lectures ago. Here's a picture of the wire chambers at the ends of the Elise TPC. And there's one interesting feature here that I want to call your attention to is the so-called gating grid here. So when we talked about drift chambers and multi-wire proportional chambers a few lectures ago, remember that there is actually two components to the signal. There's the electrons, which are low mass, that are typically then moving relatively quickly through the material. But then there's also the inverse signal from the ionization ions, which are much more massive than the electrons and therefore are drifting sort of slowly. So you can imagine that at a high rate application, like at least at the LHC, where we're having collisions pretty frequently, that there begins to be some kind of confusion built up. You know, as the electrons drift through relatively quickly, there's also in the background ions drifting in the opposite direction much more slowly. And those will partially cancel the signal. And if the ions are drifting much more slowly, they might even partially cancel the signal from like a preceding event or superimpose the positive component of the signal from a succeeding event on top of what you really want to know, which are the faster arriving electrons from the current event of interest. And one way you can deal with that problem is to have this so-called gating grid. So you basically have a set of wires, which is before the proportional chamber itself, which can basically be held each wire at an opposite polarity so that there's strong field lines in between the wires. And this will basically serve to deflect any particles from reaching the gain stage whenever this gate is energized. So imagine a slow trickle of positive ions falling through the gas. You can actually turn off that component by energizing this gate at any time when you're not expecting primary, or not primary, but you're expecting the electron signal from an event to come, you know, based on the drift velocity when that should happen relative to the collisions. So you can open this gate just long enough to allow those electrons to drift through and then re-energize the gate so that any positive ions which are floating around in the volume will get basically swept away from the gain stage. And you don't have to worry anymore about this positive component. It's kind of a clever idea to improve the robustness of this against other ions that happen to be floating around from previous events. Here's a picture from the TPC of what the events look like. They're really beautiful pictures. You can see that there's a measurement basically every few millimeters along these tracks. So the typical track will have hundreds of individual measurements. This is sort of a field day for people who want to look at precisely fitting the track parameters. If you're interested in the DEDX, each of these hits also has an amplitude associated with it. So that's very useful. By obtaining an average DEDX value out of all these hundreds of hits, you can very precisely hone in on the DEDX of the particular particle. So you have a good measurement of its momentum from the curvature of the track, and then you have many independent measurements of DEDX along the track. That's going to lead to it being really effective as a particle ID system. And then because you have so many hits, you can see things like this material interaction, which is happening here. Here we have a high energy particle, perhaps an electron, which undergoes like a hard interaction with some gas molecule in here. And you can see that there's like the original particle continuing along its direction, and then the secondary track, which is produced there. So there's just a ton of information available here for pattern recognition. And like the multi-wire proportional chamber, this is an entirely electronic thing, right? There's no compression or expansion of the gas or anything like that. With the modulo, the issue that we talked about on the previous slide, having to do with positive ions, which may be drifting around from previous events, you don't really have to do anything to get this chamber ready for the next event. So just like a multi-wire proportional chamber, it allows you to make very high fidelity images of the event, similar to what you might get out of a bubble chamber or so, but in a fully electronic way, where you don't have to worry about any issues of expansion or triggering or what have you. Here's a picture from the original time projection chamber at PEP4 of the DEDX measurements. You can see that over the momentum range between 100 MeV and a few GeV, we have very efficient separation between electrons, this more or less flat line. Remember, electrons are already sort of in the relativistic zone even here. And then you can see clearly the differing peaks from the heavier particles, the muons, the pions, kaons, protons, and even deuterons, where this would be like one proton and one neutron in a bound state. And each of them has their own little characteristic line through this space. This is the keV per centimeter of DEDX, and this is the momentum on this axis. So if you want to do an analysis where you're looking specifically at kaons, for example, one can easily draw a cut, a parallelogram basically in these different spaces to efficiently select one particle type at the momentum that you've extracted from the system. These are not just useful devices for collider detectors, but they've also been adopted by neutrino physicists as well. So the Dune FAR detector design is based on extremely large TPCs using liquid argon. So you'll see this acronym LAR-TPC, that's liquid argon time projection chamber. And that's the main technology which is going to be used to read out events at the Dune FAR detector. So Dune is this experiment that's going to be built at Fermilab over the next decade to send a high intensity neutrino beam through the Earth to a mine in Dakota, where there's this big underground detector. It's put underground in order to reduce the background from cosmic rays. And it's these types of time projection chambers, this time using a liquid, although in general, the principle of operation is not significantly different for a liquid versus a gas. It just has a higher density, which is desirable for these neutrino detectors because the rate of interaction of neutrinos, the cross-section for neutrinos to interact these detectors is, of course, quite small. You see a sort of proof of concept from an experiment at Fermilab called MicroBoon, which was basically built to study the properties of these liquid argon TPCs and prove that the technology could be usefully scaled up to be the basis of something like Dune. And you see an event display from MicroBoon here, which shows just how much information these time projection chambers can extract. Here you see a picture which looks a lot like the pictures that we saw in the early lectures of the course. Remember all those pictures from expansion chambers and nuclear emulsions where you could sort of read off the specific ionization by the density of the track and see even sometimes the Bragg peak that develops when things range out. And here you have a picture just like that, but obtained in a totally electronic way from a liquid argon TPC. So you have a muon coming in from the left side of this photograph. You see it losing a little bit of energy per unit length as it comes through the picture. And then as it reaches the end of its track here, it's slowing down, ranging out. We remember that the most of the energy of the particle is actually going to be lost in that last part of the track, given that the DEDX is increasing as the particle speed is decreasing, and that gives rise to the so-called Bragg peak there. Yeah, we can see clearly as this red spot on the picture. So that's where the DX is really high. And then the muon comes to rest and decays leptonically, giving this electron, which sort of ranges out in the material relatively quickly, with its own characteristic energy loss. So this is a really beautiful picture of the kind that you could have previously only obtained from nuclear emulsions or expansion chambers, but here is done in a fully electronic way using a liquid argon TPC. These things are going to be huge in the Dune case. So the FAR detector modules, which there are going to be several, have a fiducial volume about 10 kilotons each, so 10,000 tons each. And that's just the fiducial volume, so it excludes some of the material sort of around the edges of the TPC where full containment of the events can't be guaranteed. This is like a massive project. It involves excavating almost 1 million tons of rock to make the space for these giant experiments underground. And of course, using liquid argon means that we need to have a cryostat, like a pressure vessel that can keep the argon cold enough that it is in its liquid form. And so there's a lot of infrastructure that has to surround one of these modules in order to keep everything cold. And this whole thing has to be engineered to be robust enough to run for the 20-year lifespan that's envisioned for Dune. So really a super mega project of science. We'll probably come back and talk more about Dune later on in the course when I talk about large underground experiments a few lectures from now. Anyways, let's shift a little bit from the TPC back to the other topic that we wanted to talk about today, and that is the hunt for the top quark. So recall from a few lectures ago that the upsilon, which is interpreted to be the so-called bottomonium state, BB bar bound state, was discovered in 1977. And given that we had a very clear generation structure in the first two generations where the electron is paired with the up and down quark, the muon is paired with the strange and charm quark, we have then the third generation lepton, the tau, we have the bottom quark. And so it's almost certain that there should be a top quark, but there's really no information about what the mass of the top quark should be. Later on, when people start to do really precise measurements of the W and Z, there are some sort of higher order contributions to some of the decays of those particles that involve the top quark, like in the loops at higher order. And so you can actually extract some indirect information about the mass of the top from looking at the sort of precision corrections to the mass of the W and Z particles. But in 1977 and following years, nobody had, I mean, we hadn't discovered the Z or the W yet, for one thing, and the precision was really lacking even in the years following their discovery to make much of a constraint on the mass of the top. So in the standard model, other than this small degree of relation to the W and Z that come from these higher order diagrams, the masses of the individual quarks are really just free parameters. The theory makes no prediction about them. And so people really had no idea what to expect the mass of the top should be. Originally, people looked at sort of the distribution of masses of the existing quarks within the standard model and saw that the differences between the individual quark masses were typically a few GeV. So maybe it's also the case that the difference between the bottom and the top mass is also some few GeV, maybe 10 GeV. If the bottom quark is about 5 GeV in mass, maybe that would indicate you should expect the top quark to be 15 GeV, but it could be more. And that means that basically every collider from 1977 onward looked for the top, but it proved to be rather more difficult to find than people originally thought. I alluded to this earlier. So immediately following the discovery of the W and Z at the CERN SPPS, it continued to operate as the world's highest energy collider. The discovery of the W and Z were performed at a center of mass of 450 GeV. The machine later got a little bit more energy squeezed out of it and ended up operating by the end of its lifetime at 630 GeV. And it was considered that looking for the top quark in hadron collisions was be a good way of doing it. And these experiments were sensitive up to top quark masses of, a few tens of GeV, something like 50 GeV. UA1 originally reported that they saw an excess of events. So these would be all hadronic decays. The idea is that if the top is less massive than the W, that it should decay through the it should be visible in decays of the W to a top quark and a bottom quark. So basically what UA1 was looking for was a signature where you would have two jets that were consistent with the W mass. Of course, the jet energy resolution is not very good, so there's going to be a large continuum background underneath that of just regular standard model, like two jet events. But what they were basically looking for were events where there was a invariant mass of the two jets, which is consistent with the W boson within the experimental resolutions. And then you can look inside of the individual jet and see what its visible mass is, right? So you take all the constituent particles of the jet and build up the invariant mass of the jet. And for light quarks, or even the bottom quark, which has a mass of about 5 GeV, this sort of invariant mass of the jet is going to be less than the resolution. But if the top quark is, say, 40 GeV, that should lead to a broadening of the jet and an intended increase in the jet's invariant mass, because you're seeing all this rest energy from the, say, 40 GeV top quark going into these individual particles. They need to have a larger opening angle because of the additional momentum transverse to the jet direction that they pick up from the decay of this massive quark. So they made plots of like the invariant mass of the jet versus the invariant mass of the two jets. And they saw some clustering in that space that they originally interpreted as a top quark with a mass of about 40 plus or minus 10 GeV. However, at this point, the calculation of backgrounds in hadron collisions was really still more of an art than a science. People didn't have good Monte Carlo codes that like we have now that would just spit out the number of like two jet events that we expect at a given energy. And so they were just sort of guessing what the background to such a search would be. As they got more quantitative with their background predictions by studying the nature of hadron collisions at this energy more and more in the following years, they realized that these initial hints were not borne out by further data. And instead of discovering the top quark at the SPPS, they instead ended up producing a lower bound on the top mass, which in the case of the UA1 experiment, by the end of the running of the accelerator was at about 55 GeV. So if you thought the top was 15 GeV, this area between, say, 15 and 55 is very interesting to study, but it turns out that there is no top quark in that range. Another kind of sad, maybe forgotten chapter of physics is this E plus E minus collider at KEK, the Japanese National Particle Physics Lab. They went to quite some trouble and expense to build an E plus E minus collider at a center of mass energy of 61.4 GeV. This thing operated from 1986 until 1995, so sort of overlapping with the original run of LEP. Remember, LEP, the collider at CERN, was built to achieve the Z pole. We know that this 61.4 GeV is not energetic enough to produce the Z, so they were hoping that this new heavy quark, the top quark, would be accessible to them. If the center of mass energy is 61.4 GeV, that means that they can probe, if you're looking for top pair production, you can probe up to a top mass of about half that energy, or 30 GeV. As opposed to the SPPS, which is a hadron collider, this was an E plus E minus collider, so the events should be much easier to interpret and to fully reconstruct the final state, whereas in the case of UA1, you're trying to make these jet masses against this huge spray of tracks from the underlying event, and you have big uncertainties related to what the exact nature of the parton interaction is in the events that you're studying. Here, that is all simplified, and so this provides a very clean environment to try to go and look for the top. But unfortunately, there's just turns out not to be really any new physics to look at this energy of 61.4 GeV. It's too light to study the Z, and it's not heavy enough to produce the top. Even so, this was a fairly large effort. There were 4 detectors here, including this detector Amy, which I like for, among other reasons, because Amy doesn't stand for anything. Amy is just Amy. And the detector also had some interesting features. For example, this so-called X-ray detector outside of the tracking volume, which was designed to read the X-ray photons coming from scattering of electrons as they move through the detector. They can release Bremsstrahlung photons up to the X-ray range. And so this X-ray detector provided a good electron ID in concert with the other detectors. And so it would have been a cool detector to study new physics with if there was any new physics to study in this energy range, but unfortunately there wasn't. LEP, of course, tried to study the top quark. These are plots from the OPAL experiment, which was one of the 4 general purpose detectors at LEP. But of course, there were other analyses done by the other 3 collaborations that gave similar results. The idea here is that if the top is less than half the mass of the Z, so that's something like 46 GeV, then you should be able to pair produce tops by the decay Z to TT bar. And so you see here searches for a 6th quark or a top quark or a B prime quark as a function of mass, and basically the sensitivity of all these searches peters out at around 46 GeV, just for the simple reason that there's no longer enough energy in the Z rest mass to produce these particles if their mass is more than half of the Z. So these sort of limits fall to 0, all in the same place. You can see that they got very creative for looking at different possible decay channels of these things, including decay channels like the one that we now know that the top has to a B plus a W boson. But of course, in this case, the W boson has to be off shell because there's not enough energy to produce, to pair produce this particle with a mass greater than the W. And the exclusion limits run from a few tens of GeV up to this hard limit at about 45 GeV. So another good attempt, smart idea to try, but it turns out that the top quark's far more massive than any of these experiments would have liked it to be. So it will then fall to a new collider, which we mentioned briefly in the last lecture, called the Tevatron, in order to finally make this discovery of the top. So the Tevatron was conceived originally by Bob Wilson, the first director of Fermilab in the 70s, to double the energy of the Fermilab complex, which was at the time slated to reach 500 GeV. He wanted to push the energy of the main ring up to 1,000 GeV. The original name for this project was not the Tevatron, but the energy saver or the energy doubler. You'll see both terms used in the historical documentation. The basic idea that Wilson had was that, a lot of the operational cost of the Fermilab accelerator complex was because it was using warm magnets. So anytime that the accelerator is energized, you're using a huge amount of electrical power just to keep the current flowing through the magnets. They're built with like copper winding, so they have a low resistance per wire length, but not 0. And when you multiply it by all the magnets in this whole detector complex, it becomes quite expensive. So even with the expense to do an R&D program to build superconducting magnets of the higher field strength that would be needed to achieve these higher energies in the same ring, the idea was that in the long run, you would save on operations costs by using those superconducting magnets. And it turns out that, like, the LHC also uses superconducting magnets for the same reason. You eventually get into a regime where the power required to use warm magnets is just a showstopper as far as operating your accelerator. And so superconducting magnets from this point forward sort of become the name of the game for particle accelerators. There were ideas on the market already in the late 70s to do not a proton-proton collider, but a proton-antiproton collider. And the reason to do a proton-antiproton collider has to do with the sort of parton theory. For example, if your goal is to produce the W and Z particles, which is the goal that people had in mind around this time, right? Originally, it was hoped that this would come online in time to compete with CERN for producing these particles for the first time. The sort of tree level diagram that you have, think about Z production, is that you want a quark and an anti-quark in the initial state that collide to form a Z, which then decays according to its available decays. So if you're colliding protons with protons, there's some chance for this to happen. I mean, there are some antiprotons in the sort of C, but they typically have a lower fraction of the overall momentum than the valence quarks. So even though it's a pain in the butt to build an antiproton source, accumulate antiprotons, and then inject them into the ring to be collided with protons, you get an enormous advantage in terms of the cross-section for W and Z production by using antiprotons, because they have antiquarks in the valence band, and therefore a large fraction of their energy is carried by these valence antiquarks, and that increases by a lot the probability of these like QQ bar annihilations to produce the W and Z. So by 1978, Fermilab takes the decision that the tevatron would collide protons with antiprotons at a center of mass energy of 1.8 TeV, or 1800 GeV. And the design luminosity of this thing would be 10 to the 30th centimeters per centimeter squared per second, which is a few orders of magnitude less than what we're used to now at the LHC, but would be a very high luminosity compared to existing accelerators at the time. So the construction of all this additional infrastructure at Fermilab, the superconducting magnets, the antiproton source and its associated stuff, and then the sort of beam optics to extract the proton beam into the antiproton part and then re-inject the antiprotons into the tunnel going in the opposite direction now. That basically consumed the late 70s to the late 80s at Fermilab. The very first collisions were seen in October of 1985. So at that point, the antiproton source is operating, albeit at a very low rate of producing antiprotons. But the initial sort of data taking runs for physics took place a few years later. So the CDF detector, one of the two large general purpose detectors at Fermilab, still under construction in 1985. So those initial collisions were taken with just a subset of CDF's electronics. And the really larger data sets for physics analysis were collected starting in 1988, going into 1989. The collider first achieves its design luminosity of 10 to the 30th in 1989. So during this time, about 5 inverse picobarns were delivered to CDF at this 1800 GeV center of mass. And this was sufficient to sort of rediscover the W and Z particles at the tevatron. The antiprotons are basically the limitation on the luminosity of this accelerator was always coming from the ability to generate and store antiprotons in sufficient numbers to sort of match the intensity of the proton side as well as possible to increase the overall luminosity. The antiprotons were sort of the limiting reagent most of the time that this machine was operating. So there was the so-called Run 1A that we were just talking about. These were operations starting from these like early pilot runs in the late 80s going up until about 1993. And there was a Run 1B where there were some improvements made to the accelerator complex, as well as further developments on the detector side that we'll talk about in a moment. So there, not only had they exceeded the original design luminosity of 1E30, but even better than a factor of 10 on top of that to achieve a luminosity of 1E31 up to 2E31 by the end of Run 1B. Then there's a lengthy shutdown that runs from basically 96 through 2001. During this time, several things happened. First of all, the detectors, CDF, now joined by a sister experiment, D0, which we'll talk a little bit more about on the next few slides, were both upgraded significantly to improve their physics reach. The accelerator itself was upgraded both in order to enable a higher luminosity by improvements to the sort of anti-proton side of things, but also to be able to operate at a slightly higher energy. So the energy of 1.8 TeV that was achieved during the run one goes up to almost 2 TeV, 1.96 TeV in the center of mass for this run two. And then that run two basically lasts 10 years from 2001 until 2011. At this point in 2011, the LHC is turned on, will very quickly eclipse the Tevatron in terms of its ability to search for the Higgs boson. And we'll, of course, return to that story a little bit later. So I mentioned there were two general purpose detectors at the Tevatron. The first was CDF, which we talked about briefly already in the last lecture, talking about the early measurements on the Z boson. As we said, in the late 80s already, there had been Z's observed at CDF from collisions of the Tevatron. This is the CDF detector shown in its run two configuration, including an upgraded silicon vertex detector, as well as some other improvements that were made during this shutdown. But it's basically a 4-pi detector, very much on the UA1 mold, whose goal was to surround the interaction point with high quality calorimetry with few gaps. There's some inner tracking detectors here, and then it's surrounded with muon chambers and scintillators on the outside in order to be able to capture as many muons coming out as possible. I don't think there's anything too revolutionary about the design of this experiment. CDF was kind of the blue blood experiment at the Tevatron. It had the most sort of high profile institutions on it. It started earlier. It had a very contentious relationship with the Fermilab lab management. For the first time, the size of the experiments becomes so large in terms of like dozens of collaborating institutions and hundreds of physicists that these collaborations sort of become institutions unto themselves that start to rival the sort of power within the lab of the main lab management. So unlike maybe previous examples where there was a very clear hierarchy from the lab down to the individual experimenters who were kind of there at the pleasure of the lab, and where lab management could sort of hand out time on the various beam lines according to their own priorities. CDF and later its competitor D0 kind of become their own institution, similar in scale to a national lab of a previous era themselves. And they become very politically powerful to the extent that they can, to some extent, siphon resources about the lab from the lab that the lab might rather husband for their own projects and priorities. And so there's some interesting history to read about the relationship between these large experiments in the lab. And that kind of history is still being written, for example, at the LHC now. When you hear things about like, right now at the LHC, there's a question about what the overall schedule for the high Lumi LHC will be. And the experiments have their own opinions about what the lab should do as far as the running schedule. Depending on what part of what experiment you're talking about, they might either favor, a longer physics running before we shut down for HL-LHC upgrades or not, based on how well they think that their detectors will survive the radiation dose, et cetera, et cetera. So in a previous decade, it would have been sort of unthinkable that the experiments would actually dictate to the lab what the schedule should be. These accelerator projects were sort of their own thing, and then the users were just there to use the beam when they could. But this kicks off an era of much tighter collaboration or even competition between large experiments and their host labs, because the experiments really grow in size and funding to be comparable to the host lab itself. The other major detector that was installed at the Tevatron was called D0. The interaction points at the Tevatron were like A0, B0. I think CDF was at B0, C0, D0. And D0, sort of befitting its initial role as the sort of junior experiment, just took the name of the interaction point as the name of the experiment. D0 was originally sort of proposed in the aftermath of CDF already going forward. There's a desire to get more it's always good for experiments to have competition. It helps drive things forward. It helps to be a cross-check on any claims of discovery. And there was also a huge appetite for groups to participate in the Tevatron program that maybe weren't part of the initial CDF collaboration. So as opposed to CDF, which had, as I said, more of the sort of blue bloods of high energy physics, people like Harvard or Penn or what have you, the author list of D0 is much more sort of land grant institutions, more weighted to later arrivals on the scene, let's say, of high energy physics. And it had a sort of a different life history than CDF. By the time D0 was approved, CDF was already well underway. So D0 at first was always a few years behind. At the beginning, D0 was not envisioned to be a fully multi-purpose experiment, although in its later evolution towards Run 2, it would become that. It would add, high quality silicon vertexing and all these other capabilities to make it much more of an equal competitor to CDF. But in the beginning, the idea was, what could we do with a collider experiment that just had extremely high quality calorimetry? And the technology that was chosen for D0's calorimetry is one which is still in use today. The Atlas liquid argon calorimeter at the LHC is a clear descendant of the calorimeter at D0. And if you look at designs for detectors for like future hadron colliders, some people consider that liquid argon based calorimetry is maybe the only viable technology for that. So D0 was one of the first really large scale applications of this idea. So what is the liquid argon calorimetry of D0 look like? You have a typical unit cell here drawn in figure 4. The basic idea is that you have a bath of liquid argon. Into this bath, you sink alternating layers of absorber. So this is a metal. In the case of D0's calorimeter, it was largely depleted uranium, although there was some copper and steel used for the larger radius outer layers where this uranium would have been prohibitively expensive. Dealing with depleted uranium is kind of a pain in the ass because even though it's depleted, it's still radioactive. So you have to always be observing, radio protection standards whenever you're working with it. But it's super dense, huge nucleus. And so that makes it desirable for calorimetry, where you in general want to keep things as compact as possible. So the idea is you have this kind of alternating geometry of absorber plates, which is providing a medium for particles to shower more quickly than they would just in pure liquid argon. Then you have an insulating layer, which is basically like PCB material, and then a pad, which is connected to your readout, which is covered with a resistive coat. So the liquid argon basically plays the role of the gas in a gaseous detector. The shower of particles caused by interactions with the absorber create ionization in the liquid argon, and then by holding your pad at a potential, you can attract those ionization electrons onto the pad and read the pulse of current that's produced when they fall on there. Advantages to this approach, there are several. One is that by using liquid argon as the medium, it's a liquid, so you can circulate this liquid, keep it homogeneous throughout the volume of the calorimeter. Calorimeter builders, especially at Hadron Colliders, are always worried about how in the case of an optical detector, for example, using plastic scintillator, you're always worried about how the scintillator is aging in different parts of the detector under different radiation doses. You have differential losses of transparency, maybe even within an individual detector channel, you can have differential losses of transparency due to the details of how the ionizing radiation is breaking down the materials. And having this whole thing in basically a bath of active material, which is circulated, gets rid of a lot of those inhomogeneities. So your liquid argon is not stuck in the particular cell, but free to circulate throughout the cryostat. And this means that any issues having to do with like differential radiation damage, at least of the argon, you don't really have to worry about in this case. Compared to a gas, the higher density of the liquid also has some desirable properties as far as keeping the gain of the detector equal all the time. For gas, because the charge carrier density is relatively low, you sometimes have to worry about like rate-induced effects of depleting charge carriers from the volume, et cetera, et cetera. You'd have to have very good control over the voltages everywhere to avoid having different gains at different places. And it turns out that liquid argon is just very ideal for this purpose as well. You have a very predictable interaction of the electrons with the material in liquid argon, much more so than the gas. And its increased density increases the overall compactness of the calorimeter as well. Liquid argon is much more dense, of course, than argon gas or any other gas. So some of the same advantages that make it an attractive target, for example, for those dune TPCs, make it also an interesting medium for calorimetry. And that's what DZero are really invested in. You can see here that they sort of arranged the structure of pads in the different parts of the calorimeter. You see different cryostats here for like barrel and end cap calorimeter, different sizes of detector cells. As you move away from the interaction point, you can afford to get coarser because the occupancy of particles is smaller, and this sort of projective geometry having towers, so-called towers of the calorimeter, which point back to the interaction point, suggests that you can increase the or decrease the fineness of the segmentation as you move further away. And then these sort of projective towers shown in black and white stripes here are gained together electronically, for example, for triggering purposes. If you have a photon shower or whatever, you expect it to go basically along these lines, jets to go along these lines of constant pseudo-rapidity. And so gaining together the electronics this way allows you to add up all the energy that was deposited in one of these projective towers and use that as a sort of grouping of the electronics for the readout. So different philosophies, especially in run one, DZero being much more invested in this concept of liquid argon calorimetry and really seeing how much information you could wring out of a calorimeter dominated detector. In that sense, a little bit of a throwback to the era of detectors, which were mostly built around one specific technology and then just augmented with counters, as opposed to CDF, which took the much more UA1 inspired approach. But as they move from run one into run two, these detectors really grow to be more similar than different as they each become general purpose detectors with a full suite of instrumentation. Detecting the top quark, at this point in history, we see that the W does not decay, for example, to top plus bottom. That means that the top is likely heavier than the W, and that means that the vertex gets rearranged. Instead of W decaying to top plus bottom, we instead expect the decay top to W plus bottom, and we now know what really happens. The fact that the W has different decay modes, both hadronic and leptonic decay modes available to it, and that these things are pair produced such that there's two Ws, which don't necessarily have to decay in the same way, gives rise to kind of a rich phenomenology of possible top decays to look at. The most common decay of the W is to two quarks, two jets. And so if you pair that up with the bottom, which is a third jet, you would expect in these so-called all jet events, which make up just less than half of the total number of TT bar decays, to be basically 6 jets, 2 of which come from Bs and 2 of which can be any flavor. So these are the most copiously produced events, but they're also the most difficult to tell apart from the background, especially at a hadron collider. You're going to have a lot of multi-jet events just from interactions of the protons, even without producing top quarks. And so while these events are large in number, the mass resolution for reconstructing 6 jets is generally poor. Hadronic calorimetry is tending to give resolutions on the order of like tens of %, which means that when you're adding together 6 of these objects, you have a really wide dispersion of energies observed. So copiously produced, but perhaps the most difficult in terms of pattern recognition. On the other hand, you have dilepton events where the W's both decay leptonically. They decay leptonically on average just less than 10% of the time for each individual species of lepton, which means that if I multiply those probabilities times 2Ws, I typically have just 1% branching ratio to the different possible final states, and the ones which are opposite flavor. Of course, I have two permutations, mu plus E or E plus mu, which add together to make 2%. These events taken together are all less than 10% of the total. However, the leptons are much easier to reconstruct precisely than the jets, and that these leptonic decays also involve missing energy due to the neutrinos, which are escaping the detector undetected. So even though the branching ratio is small, this turns out to be play an important role in the discovery of the top, just because the topology of these events is amenable to triggering and reconstruction. And there are fewer backgrounds in general that produce leptons, especially different flavor leptons in the same event, as compared to the hadronic decays. Then there are the so-called lepton plus jets or single lepton cases where one W decays leptonically and the other hadronically. This, in some sense, brings the best of both worlds. They have missing energy due to one neutrino escaping. They have a lepton, and then the other side decays hadronically, but with a larger branching fraction. So these single lepton events make up about the remaining 45% of the whole. Each of these three topologies, dilepton, single lepton, and all hadronic, each has its own pros and cons, and in the end, they all contribute to the final discovery because of their unique features. Looking at the CDF analysis first, CDF had a secondary vertex detector, a silicon detector, much like the one that we looked at from UA2 already at this point in its life. And that means that the CDF experiment can directly tag the production of B jets by looking at the finite decay length that the B has before it hadronizes into a spray of particles. This is typically on the order of like hundreds of microns, and that's resolvable by the CDF vertex detector. So the idea behind the CDF analysis is to select events with and bin them by the number of jets, and then basically look at what fraction of those multi-jet events has a B tag. The efficiency of B tagging is not very good, so they're not looking for both jets to be B tagged, just one of the two. And what you should expect to see if the top is in the data and it decays via this decay to W plus B is that as we crank up the requirement on the number of jets relative to regular QCD multi-jet events, which are typically going to have two jets, maybe three if there's some radiation of, for example, a gluon involved, but relatively unlikely to produce four or more jets, whereas the top events do produce four or more jets. And those top events always have two B quarks in them, as opposed to the generic multi-jet event, which might not have any. So we should expect the fraction of events with B tags to increase as we crank up the requirement on the number of jets. And that's exactly what CDF saw. Look, for example, at this greater than equal to 4 jet bin here. They have a total of 40 events in the sample, of which fully 1/4 have secondary vertex tags compared to a background of only 1.5. So this is a high significance that there's some new process which produces lots of jets, including lots of B jets. You see here inset on the plot the proper time, basically the decay length of the B hadrons follows the distribution that you would expect if there's some real component of long-lived B jets in there. For example, you don't see events on the other side of 0, indicating that this is probably not just a resolution effect. And you can do even more. You can try to reconstruct the mass, especially in the all hadronic events, and then compare the distribution that you obtain to the distribution that you would expect for different masses of the top quark. So there's a statistical analysis done here where it shows that the most likely mass value for the top quark is somewhere between 170 and 180 GeV. And it turns out that it is exactly in this range. So they kind of nailed it there. The D0 analysis is necessarily a little less a little less performance. That has to do with the fact that D0 is lacking a silicon vertex detector at this point in its lifetime, and so they have to rely more on indirect means of tagging top events. Even though they don't have a silicon vertex detector, they do have muon chambers, and it is more likely that a jet from a B has more tendency to produce muons inside the jet than a light flavor jet, having to do with the available decay modes of the B hadrons in the jet. So you can do some amount of tagging of B jets just by looking for muons to be associated directionally with a jet. That's what these jet/mu lines in this table are. But generally, D0 is just trying to use the overall distribution of energy in the calorimeter. You see requirements on the number of jets, as well as the transverse energy of the jets, as well as the missing transverse energy, and this variable HT, which is the scalar sum of the jet PTs in the event. So they slice and dice the parameter space into these different bins according to the number of jets and the overall momentum imbalance, as well as the total amount of hadronic activity. And that enables them to look for basically a bump in the distribution of things like the HT. So you see here, this little sort of shoulder around 200 GeV in the HT distribution that's taken to be evidence of a new particle decaying hadronically with a mass of around 200 GeV in the data. Here you see in the semi-leptonic events, the 1 lepton class of events, many fewer events overall, but also a similar feature in the data around there. And then they compare the distribution of different jet mass variables to what you would expect from the background. So A and B in this picture are Monte Carlo. A is the background from QCD, where you see that typically both the 2-jet and 3-jet mass is small. These are clustered towards the upper left-hand corner of this plot, which is low 2-jet mass and low 3-jet mass, as opposed to a top quark with a rest mass of 200 GeV, which we would expect to populate the middle part of the plot. And then they show in C the actual data, where you can see that there's sort of the component that you would expect here for a top mass of around 200 GeV, plus some residual background in this quadrant, which is presumably coming from QCD multi-jet events. It's a less precise measurement than CDFs due to the different detector technology, but is also convincing enough to claim part of the discovery at the same time. Of course, their precision on the mass is worse than CDFs, and they estimate the mass to be 200 GeV in this initial paper. Over time, the mass measurements from both experiments will converge on the value that we now accept, which is about 175 GeV. So that takes us to the end of what I wanted to discuss today. We might have time for one burning question if there is one. All right, I don't see any hand, and we are in any case past our nominal stop time. So I'm going to stop here. Thanks, guys, and I will see you again at this time next week.
Thanks, Mark.